Welcome to statistics. We're going to look at some more regression line calculations we can do. This is all about the idea of, again, trying to understand a data set and get a good feeling for what's going on with the data set. So one of the things we want to do is make sure we include as much analyzing of the data that we possibly can. One piece of that is always include, regardless of your data set, you should always include the standard deviation and the mean of the individual components of the data set. In this particular data set we're going to look at here, which I have already pulled up, it has two values, an x value and a y value, as I'm going to call these, and I'll give some more details about this in a second. These are my two data sets. The first thing I'd always want to do with a data set is figure out the average or the mean and the standard deviation. For our purposes here, really the only thing we need would be the mean. So I can actually do that really quickly just by typing in equals and start to type out the word average, and then I can pick the numbers there and close my parentheses and hit enter. And then I can do the same thing. I can actually copy and paste it into the next one, and automatically, and I can just double click that and you can see that it's highlighted that entire section there. All right, so that's a pretty easy thing to do. Finding the mean of a data set is really super simple, and you should always do it anytime you're doing a real analysis of a data set. And here, this instance is actually going to be useful to us down the road. So the next thing we're going to talk about here, in a couple of previous videos, we referred to the idea of creating a scatter plot and identifying the correlation that exists. And it's always the place you want to start before you do this least squares regression line, is you want to do the scatter plot and see, does it look like it fits? If you were to draw a line, would that line fit really well? And the idea is that you want to have a tight-knit group of dots or scattering that fit together and kind of have all the same trend. If you were to draw a line, would it describe most of the dots or all the dots? The more it describes, the better the fit. And that process of creating the equation for those points, for those data points, is called the least squares regression line process that we're going to look at. Now, if you have, for those of you who are taking this course with me, the book we're using actually gives you a completely different equation from what I'm going to give you for slope. The equation it's using is actually this one on the far right here, where we have r times sy divided by sx, which is the standard deviation of y and the standard deviation of x, which we can easily find. That's not a hard thing to do at all. And then the r value. Well, the r value is only done through a particular process, which requires you to do a bunch of other processes. So if you're already using a computer system to build the r value, then using that to find the slope seems kind of silly. So what we're actually going to do here, and that's my take on it at least, so what we're actually going to do here is this is the actual least squares formula for finding the slope of our regression line. Okay, so that's the formula we're going to use, and I'm going to show you how I'm going to use that in a spreadsheet here in a second to make this process go a little bit faster for us. And then, of course, the a value, we're using a for the y-intercept and b for the slope. And the a value is y bar minus b times x bar. And if you look at this equation up here, all you got to do is subtract bx from both sides, and you essentially have the same equation. And we'll talk about the bar pieces here in just a second. But going back up to here, this is our equation. Right here, this is our least squares regression line equation, and this is read y hat, meaning the approximation for the equation that describes most of our data points, and that's equal to the y-intercept plus the slope times the x value. Notice I'm just saying the x value, not anything else, okay? And then that b value, that slope there, the rise over the run, is found by doing the summation. And that's what this E symbol right here is. This is the summation from k equal 1 to n, meaning find each of these individual values and then add them all together. And what those individual values are the individual data points. Okay. So the x data points, the y data points. And then you also have, along with that, is the mean for x and the mean for y. Okay, so you have, what you're doing there is you're taking the actual data point minus the mean, you're taking the actual data point minus the mean correspondingly with the x's and the y's, you're multiplying those together, and then you're adding all of those products together. Down here for the bottom, you're doing the same thing where you have that data point. And here we're just using the x. And then right here you have the mean just for the x again. And this equation, this formula here, is equivalent to r times s sub y divided by s sub x. In this one we can do using a spreadsheet, and it's actually a pretty straightforward process. So I'm just going to run through that with you really quick, and how you can set this up yourself in a spreadsheet. And we're probably going to have an activity of some sort to do on your own where you practice this. Now keep in mind that I'm doing this for demonstration purposes. In the real world, if you're doing statistical analysis, you're probably never going to actually figure this value for your slope by hand, because the computer systems can do it faster and more reliably than we can do it. But we're still going to try to do that. All right, now, so when, it may be kind of hard to read that, but what that first column right there, column D, says is x minus x bar, and then I have y minus y bar, and then I have x bar x minus x bar times y minus y bar, which is essentially column D times column F. And then the last column there is x minus x bar quantity squared. And those are the pieces I need for that slope there. Okay, so what I'm going to do here is I'm going to hit equals, and I'm doing x, which is this quantity right here, minus x bar, which is 324.75. And you're saying, where did that come from? It came down here. Remember, we found the average for that x, for the x's, and that's x value is x bar. Okay, so there's my value. And then I just need to do that for every single piece, right? So it's going to be that x value minus 324.75. And you're just going to do that over and over again. So I don't need to type it in every time. I can just hit control copy there, and then I can highlight all my values and hit enter, and it'll put them all in there. And you can even check. You can double click on any one of them, and you can see this is A14, cell A14, which is, if I were to type on that, it's actually going to show me that it's doing 571 minus 324.75, and that's my value there. Okay, then for a y bar, I'm going to do the same thing. I'm going to hit equals my y value minus y bar, which in this case is 2.3875. Now, some of you may be thinking that we could just, how come we just can't tap on this? Well, the way I'm copying and pasting this, Excel would actually try to continue to pick values that go down the list here. So it's easier just to kind of to do it this way for right now. There are other ways we can do this that will make it a little bit more more robust, but this is the way I'm going to choose to do it for right now. And then I'll just do the same thing over again with those pieces. And there are all my y bar values. Okay? Now what? Well, now we can do the product of those two pieces. So I'm going to do equals that piece times that one right there, those two columns. So D2 times E2, and hit enter. And then I can just copy that and paste that down the line. And that's actually the first sum I need, right? I need that to be a sum. So I can hit equal sum of this entire column here. Close my parentheses, hit enter. Let's try that again. It's not liking what I'm doing there. Let's try that again. There we go. So there is the product, all those products together. Then here, that's the sum of all those pieces rather. Then here I need to do the same thing. I need to find x bar, and I need to square it. So I need to do this cell right here and just take it to the second power. And then copy and paste that through the entire column. And then I need to do the sum of that entire column. And then the last piece, to find that slope, I'm just going to type in m there, or the equation actually uses b, so we can use b, and this is going to be equals the product of the y's and the x's divided by the x squareds. And there I get my slope. So this is theoretically the slope for my equation. And then I can go back through and I can actually figure the y-intercept as well. The slope is the big one that we're really concerned with here, and what we're going through. And you can even put a equals right there if you want to make that a little bit clearer what we just found. So b is equal to that value. Now this is the thing, we can actually come through here and highlight those values, do an insert to a scatter plot. Remember I told you always start with a scatter plot to make sure that the data actually seems like it fits really well. Okay, and I should have started with that, but I was just trying to get through that process of what we were looking at. So there's the data plots. And if you look at these data plots, you can see that there really does seem to be a downward trend for those data plots. Is it a strong fit? Does it fit really well? Well, it's definitely a negative or decreasing value there. So let's add our trend line in there. There's our trend line. Okay, definitely negative in slope. And then we can say display the equation, display the r squared value there. Okay, and when we do that, we find that the slope, it says, is negative 0.0034, which is what we just found. And then we found the slope to be 0.606. That's the r squared value, which means that my r value, let's see here, is going to be 0.778. All right, so my r value is 0.778. which is a pretty good correlation. It's not super strong, but it's also not horrible. Anything over 85, and we're pretty good. We're in a pretty good spot. 0.77, it's kind of on the verge of, well, it's a decent fit, and it might describe it decently well. And there's almost definitely a correlation between these two events. We might look at some of our outliers and see what happens if we were to eliminate an outlier. Like right here, we have an outlier, and right there we have a pretty big outlier. If we were to eliminate those outliers, those two pieces, does that give us a better fit? And that might be something we look at down the road of how does that change our values. That's right there, that's 580, the 580 value, which is right there. And then this one up here is our, let's see here if it'll tell me which one this one is. That, well, it's not going to tell me, huh? Oh well. So that looks to be about 3 something or another, so a high 3, so probably 395, so it's probably that value right there. And then this one right here, of course, is the one that 591. So we could delete those and then real quick and see what that does. And that gives us, that actually does improve our r squared value, which means that our r value would improve to let's see here, would improve all the way up to 0.85. So this does look like there is a legitimate trend in this process here, especially when we account for those outliers, all right? But even with that said, 0.778 is a pretty good r squared value. So we can say this is a negative, and actually I don't want to put there, I didn't put it in there, but I should have. If it'll let me type it in there, is make that negative 0.778, right? Because it's a negative slope, which means my regression, my correlation is a negative relationship. As one increases, the other is decreasing. Now, I'll give you some background here on this, and this will kind of maybe add some context to what we're dealing with here, is that the X column is the change in activity level, non-exercise activity, okay? B is the increase in body fat, okay? Not percentage, it's just an increase in overall body fat. How much weight did someone gain? So what this is actual data pulled from a study of, I think it was 16 individuals. And the 16 individuals were asked to do nothing more. And they would say, don't change anything, but here we're going to overfeed you for the next 12 days or something like that, 16 days. And the idea was they were to map out their energy change from the first day to the last day of the event, because they were looking to see if you just feed people more food, does their non-exercise activity level increase? Or if someone's non-activity level increases, does it also have a negation upon the excess food that they're eating, the amount that they overeat a little bit? And what we found, according to this, is that if your non-exercise activity, meaning you're sitting at your desk and your leg is bouncing up and down because you're fidgeting or something like that, or just kind of wiggling around more so than in others, that is extra energy you're expending that is not necessarily exercise, okay? Which is going to have, according to this, does actually have an effect. Meaning if you overeat just ever so mildly, but you fidget a lot, you're not necessarily going to gain a whole lot of extra weight. But if your activity level, and this is what this this negative 94 was, this individual's activity level actually went down, and as a result, they gained more weight than the person whose activity level went up. So that's what this line is like, and that makes sense. The more energy you're expending on activity, the less that food is going to be stored as fat in your body. Just a pretty good linkage there between those two pieces. So again, what we did is we went through and we found the average right here on the far left here. We found the average for the x's. We found the average for the y's, which is x bar and y bar. And then we found the difference between the individual x's and the x bar and the individual y's and the y bar. Those are what column D and E are. And then column F is the product between those differences between x's and between the quantities and their averages. And then G is the square of the differences between the independent value. And that's something else that probably should be pointed out here, is that this is the independent value and this is the dependent value. And of course, it's really easy to switch these up and see which one does this change at all when we switch the direction in which we're looking at these two things, which is sometimes what we want to do as well. It's like maybe one has a better discussion point when we look at it from the other direction. All right, and then once we found those, use that to find our slope, and then we found that slope does actually match up. So this was simply a demonstration purpose lesson on where these computer systems come up with this equation right here. I didn't want you thinking it just magically appears. There's an actual legitimate mathematical process that goes through and actually minimizes the differences between the x coordinate and the line itself. This line right here actually represents the average of all those pieces, or all those spots over there. It's the average location for all of them. So it's finding essentially the least distance between those two places, which is why we got that square business going in there, and it has a whole bunch of other pieces going into that. If you're really interested in how all this works, I encourage you to take another statistics class. We're not necessarily going to get too deep into it after this, but I want you to see where this came from. And going forward, for the most part, you're going to be expected to use a computer system to find these values for you. All right, so thank you for sticking around for a slightly longer video than normal. I hope you enjoyed this, and reach out and ask for additional supporting videos as you see that you need them. All right, take care.